Okay, 9.5, day 2, the second part of the alternating series test. Pause the video, take a couple minutes for me, and list the first 5 terms of this series. Okay, please be careful. All right, n is equal to 1, 2, 3, 4, 5. So attempt that now for me. Okay, so hopefully you got these terms: negative 1/3, minus 1/9, plus 1/27, plus 1/81, minus 1 over 243, and then the next term would be negative. Okay, so what I need you to see here is this is not an alternating series. If you recall, in an alternating series, every other term has to switch sign. So all the even terms would be positive and the odd negative, or vice versa. Okay, so how do we determine if this series converges or diverges? The alternating series test does not apply. All right, absolute and conditional convergence, that's where this comes in. If the absolute value of a series converges, then the series itself will also converge. Okay, so look at that. If we take the absolute value of a series and find that it converges, then the series itself will also converge. So let's go back to this example. Okay, so if I look at the absolute value of this non-alternating series, although the series has positive and negative terms, this just becomes 1 over 3 to the n. We'll look at this series now that we take away the negative terms of it. This is just a convergent geometric. Okay, we have a ratio of 1/3. So what does that tell me? All right, well, if the absolute value of this series converges, then the series itself must also converge. And not only that, but it converges absolutely. So what's our conclusion from here? N equals 1 to infinity of this seemingly messy looking series converges absolutely. Okay, so let's focus on this theorem here. The converse of this is not true, however. All right, so that says if we get the series to converge, then the absolute value of the series must converge as well. So let's check this out. So this series here, this is an alternating series. So by the alternating series test, I can show the limit as n approaches infinity of 1 over n is 0. The second condition, a sub m plus 1, is definitely less than a sub n. So what can I conclude? I can conclude that this alternating series converges by the alternating series test. Okay, so remember, we're investigating the converse of this absolute convergence. So we got the series to converge. Now let's look at the absolute value of the series. So the absolute value of this, remember what the absolute value does, obviously, makes all those negative terms positive. So this just becomes the series from 1 to infinity of 1 over n. Well, 1 over n, that's our harmonic series. And our harmonic series is a divergent p series. Okay. So when we look at the alternating harmonic series converges. We just proved that by the alternating series test. But when we take the absolute value of that, it's the harmonic series which itself diverges. Okay, so a series is absolutely convergent if its absolute value converges. A series is conditionally convergent if the series itself converges, but the absolute value diverges. Okay, so that's what we just showed. We showed that this series itself converges, but when we took the absolute value, it was the divergent harmonic series. So this, we would say, is conditionally convergent. And why? Because we got the original series itself to converge, but when we took the absolute value of it, the absolute value of the series diverged. Determine the convergence or divergence. Classify any convergent series as absolute or conditional. These would be very specific, your directions, okay? So if you needed to show that it was either a conditional or absolute convergence, the directions would say that. And furthermore, you have to either have an alternating series or a series that has both positive and negative terms. Okay, so looking at this, all right, it's an alternating series, so let's start with the limit as n approaches infinity. Well, when I look at this, okay, the factorial function grows faster than the exponential function. So this limit approaches infinity, and therefore this series automatically diverges by the nth term test. Done. Secondly, -1 to the n over the square root of n, okay? So what we can do is we can, let's first look at the alternating series test. It alternates of 1 over the square root of n, okay, bottom heavy, this limit approaches 0. Oop, not limit, sorry about that. A sub n plus 1 is less than a sub n. Okay, we could also, of course, if you like using the derivative, so if I wrote this as x to the negative half, f prime of x, -1/2, x to the negative 3/2. So the derivative is definitely negative for all values bigger than n is equal to 1. So what do I know? I know that this series converges, the series itself converges by the alternating series test. All right, so now let's look at the absolute value of the series to determine absolute or conditional convergence. All right, so the absolute value, that just becomes 1 over the square root of n. Okay, looking at this series, this is a divergent p-series. So a divergent p-series, since the absolute value diverges, we would say that this is conditionally convergent. Okay, so as a rule of thumb for absolute and conditional convergence, the first thing we can check the absolute value of the series. Okay? If this converges, then by the theorem, the series itself must converge. Okay? So, does this converge? If it does converge, then it's an absolute convergence. Okay? Converges absolutely. If this diverges, then it could be conditional, but we have to make sure that you have to check to see if the series itself would converge, okay? So as a rule of thumb, start with the absolute value. If you get convergence for that, converges absolutely, you don't have to check the series a sub n itself. If the absolute value diverges, then go back and use the alternating series test and see if the original series converges, then it would be conditional. All right, I'll see you in class.